So it turns out that there's a relationship between the frequency of a wave and the period. And so we know that by definition, the frequency is the number of cycles that occur per unit time or per second. And so in more general terms, we can define the frequency as the number of cycles that occur in a given amount of time per unit time. So if, for example, we counted, instead of timing how many cycles occur in 1 second, we could count how many cycles occur, let's say 10 cycles, and we could time how long it takes to complete those 10 cycles. And then we would take those 10 cycles and divide by that time that we measured with our stopwatch, and that would tell us what the frequency is. We also know that one cycle actually occurs in a time of one period, because by definition, a period is the time it takes to complete one cycle. And so if we put those values in, that one cycle occurs in a time of one period, then we have frequency is equal to 1 over the period. Another way to say this is that frequency and period are inversely related to one another. So again, the period is the time to complete one cycle. And similar to frequency, instead of timing just one cycle, what we could do to calculate the period is to time, let's say, 10 cycles. So we take and we time 10 cycles. We take that total time that it took to complete those 10 cycles, we divide by 10, and that would tell us the time it took to complete a single cycle. So another way that you could write period is the time measured over the number of cycles that occur. And one thing that as you look at the frequency and the period, you can notice that they are inverses of one another, right? So cycles over time, and here is time over cycles. So we could also rewrite this expression between frequency and period as the period is 1 over the frequency. And so we've got this nice relationship between them. If we know frequency, we can automatically determine the period, and if we know the period, we can automatically determine what the period is. I don't know if I said that right. If we know the frequency, we can determine the period. If we have the period, we can determine the frequency. So one of the other things that I mentioned that's very important is that waves travel at a particular speed. And so we'd like to know what is the speed of the wave and how is it related to the properties of the wave. And so by definition, average speed is just the distance traveled over the time interval that that distance was traveled. And so for a wave, we could ask the question, how far does a wave travel in a time of one period? And what we found in the simulation is that a wave travels a distance of one wavelength in a time interval of one period. So when we adjusted the PhET simulation to go through one cycle or one period, we found it traveled that distance of a wavelength. So plugging those values in, using the fact that the distance traveled is a wavelength, and the time interval that that wave travels that distance is a period, we see that the speed of a wave is just the wavelength over the period. If we pull out the period, 1 over the period from this expression, so speed is wavelength over period, I could factor out 1 over the period, and I realize that 1 over the period is just the frequency. So another way to write this expression for the speed of a wave is that the speed of a wave is the frequency multiplied by the wavelength. And in terms of the units that we would use, speed is measured in meters per second, standard units. Our frequency is measured in hertz, which is basically cycles per second. Our wavelength is measured in meters, and our period is measured in units of time, which would be seconds. So we're going to go back to the PhET simulation, and we're going to look at different frequency settings, and we're going to measure the wavelength, we're going to measure the period, and we're going to calculate what the speed is, and then we're going to answer these particular questions. So I am going to go out of this, and let's open up the PhET simulation, and we will adjust it according to our description. So we want to set the frequency at 1 hertz. I'm going the wrong way. So there's my frequency is 1 hertz. I'm going to go ahead and I'm going to hit play. I'm going to hit pause. I'm going to reset the timer, and I am going to step this forward so that it is at, I'll start it at the maximum. So the first thing I'm going to do is I'm going to go ahead and I'm going to measure the wavelength. So when the frequency is set at 1 hertz and the tension is on high, there's no damping, I can measure the wavelength. Here would be my 0 mark, and over here, I think that it's probably 6.1. So it's between the 6 and the 2, the 0.2, so I would say 6.1. So I'm going to come over in here and I'm going to put my wavelength as 6.1 centimeters. And now I'm going to measure what my period is. So I'm going to go ahead and I'm going to hit start, and I'm going to have this go through 1 cycle. So I'm going to go all the way down, and I'm going to go all the way back up again to where I was. There we go. And I get a period of 1 second. 1 second. And that makes sense because the period and the frequency are inversely related to one another. So in this particular case, 1 over 1 is just 1. So that's exactly what I would expect. Let's also calculate the speed, which is the frequency, which is 1 hertz, times the wavelength, which is 6.1 centimeters. And I end up getting 6.1 centimeters per second because hertz is cycles per second, and I end up getting units of centimeters per second. All right, we're going to do the same thing. We're going to adjust this frequency to 1.2. So let's go ahead and put the frequency, did I say 1.2? Yeah, 1.2. Set this up to 1.2. We're going to repeat this. I'm going to go ahead and hit play. I'm going to pause it, reset. I'm going to have it set to 0 again. So here we go. Let's measure the wavelength. So I think my wavelength here, starting at 0, is probably 5.1. I would say it's like right there, maybe a little bit more. It might be 5.15, something like that. Let's just say it's 5.1 centimeters. And we need to measure what the period is. So I'm going to hit the stopwatch, and I'm going to go through 1 cycle, and we'll measure the period. I'm going to go all the way down, and I'm going to go all the way back up again. There we go. And I'm getting 0.82 seconds. So let's go ahead and calculate the speed. So 1.2 hertz multiplied by 5.1 centimeters equals, and I have to grab my calculator real quick. So 1.2 times 5.1 gives me 6.12 centimeters per second. All right, adjust this frequency to 1.5. So here we go. We're going to adjust this to 1.5. See if I can do it quickly this way. I'm going to hit play, let it go through a couple cycles. Let me step it forward. There we go. So let's measure the wavelength. So here's my starting point. Here's my ending point. Here I would say it's between 4 and 4.2. It's a little closer to 4.2. I'm going to say this is 4.15 centimeters because it's a little bit bigger than 0.1, and it's not quite 0.2. Oops. And let's go ahead and measure the period. So I'm going to reset this. We're going to go all the way through cycles. There we go. Oops, I forgot to hit play. All right, one more time. Let's go all the way down and then back up again, and I get 0.68 seconds. And now I can measure the speed, which is the frequency, 1.5 hertz, times the wavelength, 4.15 centimeters. And this is equal to, I got to get my calculator out again, 1.5 times 4.15, and I get 6.2 per second. So maybe my estimate here for that wavelength was a little bit high, but that's okay. We'll leave it the way that it is, and we'll go ahead and we'll answer some questions now. So we've got all these expressions. So as the frequency increases, so here our frequency got bigger and bigger and bigger, what happened to the period? So as we look at the period, as the frequency goes up, the period goes down, and that makes sense because they are inversely related to one another. As the frequency increases, what happens to the wavelength? So here my frequency is getting bigger as I go down, and my wavelength is getting smaller So here it appears that for this particular wave on this string, as the frequency got bigger, the wavelength got smaller, and so there's also an inverse relationship there. As the frequency increases, what happens to the speed of the wave? Well, as I look at the speed of the wave, it's 6.1, 6.12, 6.2. I would say just, using this and realizing it's a simulation and we're having to do some estimates here in terms of what that ruler can actually read, these values for the speeds are staying about the same. So as the frequency increases, the speed of the wave stays constant. And it turns out that the speed of a wave is fixed for a particular medium. So this particular string has a particular mass associated with it. It has a certain tension associated with it. So as long as you don't change the properties of the medium itself where the wave is traveling, the wave speed will stay the same. Now if I change the settings so that the tension is lower, then the wave speed would actually change. And we're going to see that a little bit later. So let's look at another example. This one is not so much a wave traveling on a string, but it sort of reiterates this idea of frequency and wavelength and so on. So we have a child that's on a swing, and the child moves to and fro. So you've probably all watched a child on a swing before you've swung on a swing. It says that the child moves back and forth 5 times in 20 seconds. What is the frequency of vibration? So anything that has this oscillatory motion, we could calculate the frequency for. And so we know that frequency is the number of cycles that occur and divided by the time to complete those cycles. The number of cycles is 5. That's the back and forth motion of 5 times. The time is 20 seconds. And so I can take 5 cycles over 20 seconds, and I get 1/4 cycles per second is hertz, so that's 0.25 hertz. We can also determine what the period of the motion is, the time to complete one cycle, and we know that period is 1 over the frequency, so 1 over 0.25 hertz is 4 seconds. And so there is this inverse relationship between those two quantities. We also could have calculated the period by taking the total time of 20 seconds and divided by the number of cycles, 5, and of course that would also give us 4. Here we have another example. In this particular case, it's actually a wave on a string. So I have a wave on a string that oscillates up and down 15 times, that's the number of cycles, in a time of 5 seconds. It says the distance between wave crests is 8 centimeters. So this is similar to that simulation that we just looked at. What is the frequency of oscillation? So we know the number of cycles is 15. We know the time to complete those cycles is 5. The frequency is the number of cycles divided by the time to complete those cycles. So that would be 15 cycles over 5 seconds, which would give us 3 hertz. What is the wavelength of the wave? Well, this is not something we have to calculate. The fact that they have given us the distance between wave crests tells us that the wavelength is 8 centimeters. We can also determine the speed of the wave, and we know the speed of the wave is the frequency of the wave multiplied by the wavelength. We know the frequency of the wave is 3 and the wavelength is 8. So the frequency is 3 hertz times 8 centimeters, which gives us 24 centimeters per second. So here, these are just a couple of examples of how we could calculate the speed of a wave, how we measure the wavelength of a wave, and figure out frequency.